In computer science, functional programming is a programming paradigm, a style of building the structure and elements of computer programs, that treats computation as the evaluation of mathematical functions and avoids changing state and mutable data. It is a declarative programming paradigm, which means programming is done with expressions. In functional code, the output value of a function depends only on the arguments that are input to the function. So calling a function f twice with the same value for an argument text will produce the same result f each time. Eliminating side effects, i.e., changes in state that do not depend on the function inputs, can make it much easier to understand and predict the behavior of a program, which is one of the key motivations for the development of functional programming. Functional programming has its roots in lambda calculus, a formal system developed in the 1930s to investigate computability. The Entscheidungsproblem, function definition, function application, and recursion. Many functional programming languages can be viewed as elaborations on the lambda calculus. Another well-known declarative programming paradigm, logic programming, is based on relations. In contrast, imperative programming changes state with commands in the source language, the most simple example being assignment. Imperative programming does have functions, not in the mathematical sense, but in the sense of subroutines. They can have side effects that may change the value of program state. Functions without return values therefore make sense. Because of this, they lack referential transparency, i.e., the same language expression can result in different values at different times depending on the state of the executing program. Functional programming languages, especially purely functional ones such as Hope and Rex, have largely been emphasized in academia rather than in commercial software development. However, prominent programming languages which support functional programming such as Common Lisp, Scheme, Clojure, Wolfram Language, Racket, Erlang, OCaml, Haskell, and F# have been used in industrial and commercial applications by a wide variety of organizations. Functional programming is also supported in some domain-specific programming languages like R, J, K and Q from KX Systems, XQuery, XSLT, and Opal. Widespread domain-specific declarative languages like SQL and Lex, YACC use some elements of functional programming, especially in issuing mutable values. Programming in a functional style can also be accomplished in languages that are not specifically designed for functional programming. For example, the imperative Perl programming language has been the subject of a book describing how to apply functional programming concepts. This is also true of the PHP programming language. C#3.0 and Java 8 added constructs to facilitate the functional style. The Julia language also offers functional programming abilities. An interesting case is that of Scala. It is frequently written in a functional style, but the presence of side effects and mutable state place it in a gray area between imperative and functional languages. History. Lambda calculus provides a theoretical framework for describing functions and their evaluation, although it is a mathematical abstraction rather than a programming language. It forms the basis of almost all functional programming languages today. An equivalent theoretical formulation, combinatory logic, is commonly perceived as more abstract than lambda calculus and preceded it in invention. Combinatory logic and lambda calculus were both originally developed to achieve a clearer approach to the foundations of mathematics. An early functional-flavored language was Lisp, developed by John McCarthy while at Massachusetts Institute of Technology for the IBM 700 and 7000 series scientific computers in the late 1950s. Lisp introduced many features now found in functional languages, though Lisp is technically a multi-paradigm language. Scheme and Dylan were later attempts to simplify and improve Lisp. Information processing language is sometimes cited as the first computer-based functional programming language. It is an assembly-style language for manipulating lists of symbols. It does have a notion of generator, which amounts to a function accepting a function as an argument, and, since it is an assembly-level language, code can be used as data, so IPL can be regarded as having higher-order functions. However, it relies heavily on mutating list structure and similar imperative features. Kenneth E. Iverson developed APL in the early 1960s, described in his 1962 book A Programming Language. APL was the primary influence on John Backus's R. In the early 1990s, Iverson and Roger Huey created J. In the mid-1990s, Arthur Whitney, who had previously worked with Iverson, created K, which is used commercially in financial industries along with its descendant Q. John Backus presented it in his 1977 Turing Award lecture, Can Programming Be Liberated from the von Neumann Style, a functional style in its algebra of programs. He defines functional programs as being built up in a hierarchical way by means of combining forms that allow an algebra of programs in modern language. This means that functional programs follow the principle of compositionality. Backus's paper popularized research into functional programming, though it emphasized function-level programming rather than the lambda calculus style which has come to be associated with functional programming. In the 1970s, ML was created by Robin Milner at the University of Edinburgh, and David Turner initially developed the language SASL at the University of St. Andrews and later the language Miranda at the University of Kent. Also in Edinburgh in the 1970s, Birstall and Darlington developed the functional language NPL. NPL was based on clean recursion equations and was first introduced in their work on program transformation. Birstall, McQueen and Sanella then incorporated the polymorphic type checking from ML to produce the language Hope. ML eventually developed into several dialects, the most common of which are now OCA-ML and Standard ML. Meanwhile, the development of Scheme, as described in the influential Lambda papers and the 1985 textbook Structure and Interpretation of Computer Programs, brought awareness of the power of functional programming to the wider programming languages community. In the 1980s, Per Martinello F. developed intuitionistic type theory, which associated functional programs with constructive proofs of arbitrarily complex mathematical propositions expressed as dependent types. This led to powerful new approaches to interactive theorem proving and has influenced the development of many subsequent functional programming languages. The Haskell language began with a consensus in 1987 to form an open standard for functional programming research. Implementation releases have been ongoing since 1990. Concepts. A number of concepts and paradigms are specific to functional programming, and generally foreign to imperative programming. However, programming languages are often hybrids of several programming paradigms, so programmers using mostly imperative languages may have utilized some of these concepts. First class and higher-order functions. Higher-order functions are functions that can either take other functions as arguments or return them as results. In calculus, an example of a higher-order function is the differential operator, which returns the derivative of a function. Higher-order functions are closely related to first-class functions in that higher-order functions and first-class functions both allow functions as arguments and results of other functions. The distinction between the two is subtle. Higher order describes a mathematical concept of functions that operate on other functions, while first class is a computer science term that describes programming language entities that have no restriction on their use. Higher-order functions enable partial application or currying, a technique in which a function is applied to its arguments one at a time, with each application returning a new function that accepts the next argument. This allows one to succinctly express, for example, the successor function as the addition operator partially applied to the natural number 1. Pure functions. Purely functional functions have no side effects. This means that pure functions have several useful properties, many of which can be used to optimize the code. If the result of a pure expression is not used, it can be removed without affecting other expressions. If a pure function is called with arguments that cause no side effects, the result is constant with respect to that argument list, i.e., if the pure function is again called with the same arguments, the same result will be returned. If there is no data dependency between two pure expressions, then their order can be reversed, or they can be performed in parallel and they cannot interfere with one another. If the entire language does not allow side effects, then any evaluation strategy can be used. This gives the compiler freedom to reorder or combine the evaluation of expressions in a program. While most compilers for imperative programming languages detect pure functions and perform common sub-expression elimination for pure function calls, they cannot always do this for pre-compiled libraries, which generally do not expose this information, thus preventing optimizations that involve those external functions. Some compilers, such as Goose, add extra keywords for a programmer to explicitly mark external functions as pure to enable such optimizations. Fortran 95 also allows functions to be designated pure. Recursion iteration in functional languages is usually accomplished via recursion. Recursive functions invoke themselves, allowing an operation to be performed over and over until the base case is reached. Though some recursion requires maintaining a stack, tail recursion can be recognized and optimized by a compiler into the same code used to implement iteration in imperative languages. The Scheme language standard requires implementations to recognize and optimize tail recursion. Tail recursion optimization can be implemented by transforming the program into continuation passing style during compiling, among other approaches. Common patterns of recursion can be factored out using higher-order functions, with catamorphisms and anamorphisms being the most obvious examples. Such higher-order functions play a role analogous to built-in control structures such as loops in imperative languages. Most general-purpose functional programming languages allow unrestricted recursion and a Turing complete, which makes the halting problem undecidable, can cause unsoundness of equational reasoning, and generally requires the introduction of inconsistency into the logic expressed by the language's type system. Some special-purpose languages such as Coq allow only well-founded recursion and are strongly normalizing. As a consequence, these languages fail to be Turing complete, and expressing certain functions in them is impossible. But they can still express a wide class of interesting computations while avoiding the problems introduced by unrestricted recursion. Functional programming limited to well-founded recursion with a few other constraints is called total functional programming. Strict versus non-strict evaluation. Functional languages can be categorized by whether they use strict or non-strict evaluation. Concepts that refer to how function arguments are processed when an expression is being evaluated. The technical differences in the denotational semantics of expressions containing failing or divergent computations. Under strict evaluation, the evaluation of any term containing a failing subterm will itself fail. For example, the expression print length will fail under strict evaluation because of the division by zero in the third element of the list. Under lazy evaluation, the length function will return the value 4, since evaluating it will not attempt to evaluate the terms making up the list. In brief, strict evaluation always fully evaluates function arguments before invoking the function. Lazy evaluation does not evaluate function arguments unless their values are required to evaluate the function call itself. The usual implementation strategy for lazy evaluation in functional languages is graph reduction. Lazy evaluation is used by default in several pure functional languages, including Miranda, Clean, and Haskell. Hughes 1984 argues for lazy evaluation as a mechanism for improving program modularity through separation of concerns. by easing independent implementation of producers and consumers of data streams. Launchbury 1993 describes some difficulties that lazy evaluation introduces, particularly in analyzing a program's storage requirements, and proposes an operational semantics to aid in such analysis. Harper 2009 proposes including both strict and lazy evaluation in the same language, using the language's type system to distinguish them. Type systems, especially since the development of Hindley-Milner type inference in the 1970s. Functional programming languages have tended to use typed lambda calculus, as opposed to the untyped lambda calculus used in Lisp and its variants. The use of algebraic data types and pattern matching makes manipulation of complex data structures convenient and expressive. The presence of strong compile time type checking makes programs more reliable, while type inference frees the programmer from the need to manually declare types to the compiler. Some research-oriented functional languages such as Coq, AGDA, KN, and Epigram are based on intuitionistic type theory, which allows types to depend on terms. Such types are called dependent types. These type systems do not have decidable type inference and are difficult to understand and program with. But dependent types can express arbitrary propositions in predicate logic. Through the Curry-Howard isomorphism, then, well-typed programs in these languages become a means of writing formal mathematical proofs from which a compiler can generate certified code. While these languages are mainly of interest in academic research, they have begun to be used in engineering as well. ComCert is a compiler for a subset of the C programming language that is written in Coq and formally verified. A limited form of dependent types called generalized algebraic data types can be implemented in a way that provides some of the benefits of dependently typed programming while avoiding most of its inconvenience. GADTs are available in the Glasgow Haskell compiler, in OCaml and in Scala, and have been proposed as additions to other languages including Java and C#. Referential transparency. Functional programs do not have assignment statements, that is, the value of a variable in a functional program never changes once defined. This eliminates any chances of side effects because any variable can be replaced with its actual value at any point of execution. So, functional programs are referentially transparent. Consider C assignment statement x equals x * 10. This changes the value assigned to the variable x. Let us say that the initial value of x was 10, then two consecutive evaluations of the variable x will yield 10 and 100 respectively. Clearly, replacing x equals x * 10 with either 10 or 100 gives a program with different meaning, and so the expression is not referentially transparent. In fact, assignment statements are never referentially transparent. Now, consider another function, such as int +1, return x + 1, is transparent, as it will not implicitly change the input x and thus has no such side effects. Functional programs exclusively use this type of function and are therefore referentially transparent. Functional programming. In non-functional languages it is possible to use a functional style of programming in languages that are not traditionally considered functional languages. For example, both D and Fortran 95 explicitly support pure functions. JavaScript, Lua and Python had first-class functions from their inception. Amrit Prem added support to Python for lambda, map, reduce, and filter in 1994, as well as closures in Python 2.2. Though Python 3 relegated reduce to the functools standard library module. First-class functions have been introduced into other mainstream languages such as 5 Philippine pesos and 30 centavos, Visual Basic 9, C# 3.0, and C++ 11. In Java, anonymous classes can sometimes be used to simulate closures. However, anonymous classes are not always proper replacements to closures because they have more limited capabilities. Java 8 supports lambda expressions as a replacement for some anonymous classes. However, the presence of checked exceptions in Java can make functional programming inconvenient, because it can be necessary to catch checked exceptions and then rethrow them, a problem that does not occur in other JVM languages that do not have checked exceptions, such as Scala. In C#, anonymous classes are not necessary, because closures and lambdas are fully supported. Libraries and language extensions for immutable data structures are being developed to aid programming in the functional style in C#. Many object-oriented design patterns are expressible in functional programming terms. For example, the strategy pattern simply dictates use of a higher-order function, and the visitor pattern roughly corresponds to a catamorphism, or fold. Similarly, the idea of immutable data from functional programming is often included in imperative programming languages. For example, the tuple in Python, which is an immutable array.